And now, for a pretty big deal in a room of pretty big deals, we really have to pull out all the stops today because our keynote speaker knows a bit about celebrating metrological milestones. He was there for the 100th anniversary of the Metre Convention, and there is also the small matter of his Nobel Prize for Physics. Now, that was awarded to Professor William Daniel Phillips in 1997 for his groundbreaking work on laser cooling and trapping of atoms that had a huge impact on precision measurement and atomic clocks. So he'll be sharing with us the secret of PSYOPs? No? Okay, fine. I thought I'd give it a go. But they're everywhere, shaping everything. So, Professor Phillips, I am not alone in saying that it is a real honor to have you with us. Over to you.
Well, thank you very much for that kind introduction. Can we put my laptop up on the screen? Thank you. A new measure, the revolutionary quantum reform of the modern metric system. It is World Metrology Day. What a wonderful time to celebrate 150 years of the BIPM, 150 years of international metrology. And earlier this year, in this very place, the UNESCO inaugurated the International Year of Quantum Science and Technology, and I want to emphasize the close connection between these two celebrations because more and more the international system of units is becoming quantum-based, and I'm going to tell you a little bit about that story. But first I want to emphasize how pleased and how honored I am to be representing the National Institute of Standards and Technology and the United States of America here at the 150th anniversary of the Convention du Metre and the creation of the BIPM. The United States was one of those 17 original signers of the Convention du Metre. And it's true that the United States sometimes takes a little bit of justified criticism in not embracing fully the metric system, at least in its daily life. But we have been from the very beginning an extremely strong supporter of international metrology and of the mission of the BIPM, and we have been metric since even before the Convention du Metre, at least legally. As you've heard, I was here in Paris for the 100th anniversary of the Convention du Metre and for the 125th. At the time of the 100th anniversary, I was a graduate student and attending one of my first international meetings, in this case about metrology. Atomic Masses and Fundamental Constants 5 was the name of the conference. And at that time, France issued a special commemorative stamp for the 100th anniversary. And as you'll see on the stamp, at the center is the meter. At the top of the wheel and in the center of the nucleus of this stylized atom, and also the wavelength shown there at the bottom of the stamp, all affirm the importance of the Convention du Metre as the center of metrology. The conference was introduced, or at least he wasn't able to be there, but the famous French physicist Alfred Kastler reminded us at the beginning of the conference of the ancient story of the Tower of Babel as told in the Bible, and suggested that in addition to the proliferation of language, that this event had resulted in a proliferation of standards of measurement. And he said, while the proliferation of languages was still something that we labored under, that when it comes to units of measurement, the curse has been charmed away, and a universal system has now been established. And of course, he was talking about the Système International d'Unité, the International System of Units. Well, that was the 100th anniversary. At the 125th anniversary, one of the highlights of the visit was a chance to actually see in person the International Prototype Kilogram. And here I am with Rich Davis, one of the heroes of international mass metrology, standing in front of the triple glass globes that contain the International Prototype Kilogram. That was a tremendous thrill for me, to see the actual kilogram. Now, much of the story of international metrology has been in making measurement more accessible, more useful, and more accurate. And this recent quantum reform of the SI is only the latest example of this. And you've been hearing about it, and the International System of Units with its 7 base units now, as you've heard, is based upon defining constants of nature. Now, in order to understand how this comes about, I'm going to tell the story of the meter itself, of the metrology of length, a short version of that history. But the story is one that is truly instructive of the way in which the International System of Units has evolved today. The early approach to length was to use the human body. A fathom was a person's wingspan. A cubit was the distance between the elbow and the fingertips. A foot was a foot. This was really convenient because you always had your standards of measurement with you. On the other hand, it was not particularly consistent. If you were buying fabric from a short fabric merchant, you might not get what you expected. So even ancient people had an approach to fix this problem, and that was to decide on a single person and use the body of that single person. And in ancient Egypt, that was the pharaoh. But they were more clever than that, because the pharaoh was not always around, especially when you were building the pyramids. And so they produced a stone replica of the pharaoh's forearm, and this became the artifact standard of measurement. And as you've heard, the production of the pyramids was rather remarkably accurate. In fact, the baselines are square to just a few hundredths of a percent, and the angles are correct to a few seconds of arc. It's really a remarkable achievement, achieved by professional metrology. And these people were really serious about their metrology, because the engineers in the field who were building the pyramids were using secondary standards made out of wood that had to be calibrated every month against the stone standards, on pain of death if you did not recalibrate. So these people really were serious about metrology. And the results, as you can see, were quite remarkable. In a more modern era, similar artifacts were common throughout Europe, for example, often cemented into the walls of the town square. And here we see a tourist, in fact, the spouse of a metrologist, who's comparing her fathom against the official fathom of Regensburg. And it looks like this would probably be a very good place to buy things by length. But if you were to go into the surrounding towns of the area, you would find a completely different set of measurement standards. And this was exactly the problem that the French revolutionaries saw as being ripe for solution, using the philosophy, the principles of the revolution. They decided to make length democratized and defined a new standard of length called the meter, which was 1/10,000,000th of the distance, the meridian between the North Pole and the equator, along a meridian, just to make sure that everything was completely universal, the meridian that goes through Paris. What did they do? Well, first of all, the philosophy here, as you've heard before, and is commemorated in these memorial coins, was to produce a system of units that was good à tous les temps, à tous les peuples, for all time, for all people. And in this medal, you see a mythological creature who is measuring the earth. And that's exactly what they did. They sent out teams of surveyors, astronomers, to measure the distance in the old units between Barcelona and Dunkirk, and then extrapolated to the rest of the meridian. And with these new units, they knew the length of this new measure, the meter, that was to be the measure of all things. But you know what they did? They did the same thing that the ancient Egyptians did. They created an artifact. This platinum rod became the meter of the archives, based upon that measurement of the earth, but a more practical way of using the meter. And it was deposited in the archives of France in 1799, at the end of the 18th century, and it became the standard of length for all of France. In that wonderful year of 1875, the Convention du Metre mandated the creation of a new standard. The meter, the length of that meter of the archives, was enshrined as the distance between two scratches on this platinum iridium rod, and it became the meter for the entire world. But this is the end of the 19th century now, and physicists had learned that light was a wave, and they had learned how to make instruments like this interferometer, this Michelson interferometer, that allowed the precise measurement of length or displacement in terms of the wavelength of light. This wonderful instrument, when this mirror is moved by a quarter of a wavelength of light, approximately 2/10 of 1/1,000,000th of a meter, changes the interference pattern produced from having a dark spot at the center to having a bright spot at the center. 2/10 of a 1,000,000th of a meter. The scratches on the international prototype meter have a width of approximately 20/1,000,000ths of a meter. So now you have the uncomfortable situation where you have a technology, optical interferometry, that can measure length better than the definition of length itself. And so people began to measure length using light in a sort of de facto way, where the wavelength of light had become the de facto but not the legal standard of measurement. It took some decades, because of the conservative nature of metrology, which extends till today, to redefine the meter in terms of the wavelength of light. To embrace this new technology, they defined in 1960 the wavelength of light from a krypton lamp. The lamp is shown here. When you excite the lamp electrically, it gives off a beautiful orange color light, and the wavelength of that orange light was defined in 1960. The year, by the way, in which the laser was invented. Well, that enshrinement of krypton was commemorated in this stamp. You see krypton here, and this was the realization of a dream of scientists from the 19th century. We've heard earlier from, where is Miss Kelvin? So Lord Kelvin was, along with James Maxwell, was one of the people who advocated the use of natural standards as standards of measurement. And Maxwell said, thinking already in the 19th century that light would be a good standard, that such a standard would be independent of any changes in the dimension of the Earth, and then jokingly said, and should be adopted by those who expect their writings to be more permanent than that body. Well, this krypton lamp was soon superseded by the fact that lasers were making light that was more pure than the light that came out of the krypton lamp. And lasers like this, a helium neon laser stabilized to a particular transition in molecular iodine, became the unofficial standard of length, because again we had a situation where the technology had outrun the definition. And that uncomfortable situation again needed to be corrected. And people were using this de facto standard of length again, and obviously we needed to redefine the meter. And the obvious way to redefine the meter would have been to define the wavelength of the light coming out of an iodine-stabilized helium neon laser. But fortunately, the world metrology community did not do the obvious thing. Instead, they did something beautiful and brilliant. They defined the speed of light. And this is the wonderful story that has become the uniform story for the SI. So what does it mean to define the speed of light? The new definition was that the meter is the length of a path traveled by light in vacuum during a time interval of this fraction. And the denominator of this fraction is then, by definition, the speed of light in meters per second. Now here's the beauty. If we define the speed of light and we measure the frequency of the light, and by 1983 people had learned how to measure the frequency of light, you immediately know what the wavelength is. So it doesn't matter what the light is. If you measure its frequency and if you define the speed of light, you have a ruler that is calibrated in SI units. Now the beauty of this is that if someone makes a better laser, and they did, if someone develops a new way and better way of measuring the frequency of light, and they did, it's immediately incorporated into this new definition. And the definition gets better as the technology gets better, but the definition itself doesn't need to be changed. Well, here are two of the heroes. They got the Nobel Prize in 2005 for making better lasers, for developing better techniques for measuring the frequency of those lasers. And we have this beautiful culmination of the story of length, that we started from length as an artifact, turned into length being defined by a natural constant of nature, that is the wavelength of krypton, and finally, the real beauty is in defining length by defining a fundamental constant of nature, the speed of light. And we should never need to change again. Now, the rest of the story. In May 20th, this very day in 2019, the international metrology community brought the beauty of this way of defining a constant, by defining a fundamental constant of nature, brought this beauty to the kilogram, and for that matter to the ampere, the Kelvin, and the mole. What a wonderful day. Well, why was this done? Why did it have to be done, particularly to the kilogram? The kilogram is the star of this story. Why and how? Well, why goes back to the revolutionaries of the French Revolution. In the spirit of making the meter the measure of all things, they wanted to make a kilogram, the new unit of mass, based on the meter. And so they defined this new unit of mass, the kilogram, as being the mass of the amount of water that you could put into a cube that was 1/10 of a meter on a side, what we call a liter. So the mass of a liter of water is defined to be a kilogram. Well, it turned out that it wasn't that easy to get exactly 1 liter of water, and there were issues having to do with the density of water depending on temperature. And so, guess what? They made an artifact. They manufactured a platinum cylinder that's called the kilogram of the archives, as closely as possible to the mass of a liter of water, and deposited it in the archives of France in 1799. Not too long ago, I made a visit to the archives of France with Terry Quinn, former director of the BIPM, and there I am holding the kilogram of the archives. Not just looking at it through the doors in the BIPM, but, I mean, of course, it's not it's not the kilogram anymore, but for years it was the unit of mass for the country of France. And there I am holding this little bit of platinum, which, of course, in 1875 was replaced with the kilogram for the world, the International Prototype Kilogram, which you see under these glass covers. And of course, this is what we're celebrating today, the Convention de Metre, which, along with a new definition of the meter, a new prototype meter, gave us a new prototype kilogram. So this is, until just a few years ago, the definition of the kilogram for the world. It's the unit of mass equal to the mass of the international prototype of the kilogram. Now, my friends, think about this. It's the 21st century. We have a unit of mass that is an artifact, a piece of actual metal that was made in the 19th century, but it was based upon the object that you've seen that was made in the 18th century. In fact, they made a lot of copies of the kilogram, as identical as they could, and the one that was closest in mass to the kilogram of the archives became the International Prototype Kilogram. But to imagine that we are in the 21st century using this artifact whose history goes back to the 18th century is truly scandalous. If somebody left a fingerprint on the International Prototype of the Kilogram, all of you would lose weight, and not in a way that would be helpful at all. So this is intolerable. We had to change this scandalous situation, and of course, we don't leave fingerprints on the International Prototype of the Kilogram, but that kilogram is changing nevertheless. Here is a plot of the relative mass of a number of the identical copies that were made at the same time over a period of many decades. And you'll see that almost all of these copies are drifting, becoming heavier relative to the International Prototype Kilogram. Now, you might think, it doesn't take too much imagination to think that maybe the International Prototype Kilogram is getting lighter rather than all the other ones getting heavier. Obviously, some mix of some things getting heavier and some things getting lighter. But of course, the International Prototype of the Kilogram cannot get lighter. It would be illegal for the International Prototype Kilogram to change mass because it is, by definition and by law, a kilogram. Well, that's not a very good situation, and that has to be changed. And so we wanted to change it in a way that reflected the same beauty that was used in the definition of the meter. So for defining the meter, we defined the speed of light. What constant shall we use for the kilogram? Well, to show that, let me remind you of what is surely the most famous equation of all time. E equals mc squared. Einstein's famous relation tells us that the energy of an object at rest is equal to the rest mass of that object times the square of the speed of light. Now, there's another equation, not quite as famous, but well known to many people, that the energy of a photon is equal to Planck's constant times the frequency of the light that represents that photon. So we just take those two equations and set them equal to each other and solve for the mass, and we find that the mass is equal to Planck's constant times the frequency divided by the square of the speed of light. Now, what does this equation mean? Imagine you had an object, let's say an atomic nucleus, that was radioactive, and it emitted a gamma ray, a photon of high-frequency light, and you could measure the frequency of that gamma ray. Then this equation tells you the change in the mass of that nucleus because it emitted a photon. Essentially, the experiment would be that of weighing a photon. Well, we don't weigh photons. Actually, we do. It's just that we can't do it well enough to use it as a mass standard. This is simply to indicate to you how defining Planck's constant can give us a standard of mass. Instead, we do it in a different way, a way that's very near and dear to my heart because, as you've heard, I've been involved in laser cooling, and you have to start with a sample of laser-cooled atoms. So imagine that you've got an atom at rest in the ground state, and you shine in a laser that can excite the atom, and you know what the frequency of the light is, so that means you know the energy of the photons, h times the frequency, and you know the momentum of the photons, which is h, Planck's constant, divided by the wavelength. And you know the wavelength because you know the speed of light. Everything is known very well. The light is absorbed by the atom. The atom goes into the excited state, absorbing the energy of the photon, but it also absorbs the momentum of the photon. So now the atom is moving with a velocity corresponding to the conservation of momentum. So that velocity is Planck's constant divided by the mass and the wavelength. Solving for the mass, we have that the mass of the atom is equal to Planck's constant divided by the velocity and the wavelength. Now, it turns out that we have techniques for measuring the velocity, and the cartoon version that I've shown you here is an oversimplification of how we do it, but I don't have time to tell you how it's really done. Ask me afterwards, and I'll be happy to explain it to you. But the point is, we can measure all these things, and that means we know what the mass of the atom is. It's usually rubidium. We know what the mass of the atom is in kilograms. Now, we're used to knowing about what masses of atoms are in atomic mass units, but now we know what the mass of the atom is in kilograms. So all we need to do is multiply that up, getting lots and lots of atoms together whose mass we know, and now we've got a kilogram. Well, how that's done is a wonderful story all of its own. At PTB, they make near perfect spheres of single crystal silicon that's also isotopically pure. These are the most spherical objects ever made anywhere on Earth. And you use X-ray interferometry to give you the spacing between the atoms. You use optical methods to measure the dimensions of this sphere. And if you know what the spacing of the atoms in the perfect crystal is, and you know what the size of the sphere is, you know how many silicon atoms are in this sphere, and you know the mass of the silicon atom in kilograms because you've compared it to rubidium and you measured the mass of the rubidium. So now you know the mass of this object, and you can make it be a kilogram, but it's not an artifact. Anybody can make one of these things, as we've heard, if they have the right techniques and the laboratory skills. This is one of the ways that today we realize the new definition of the kilogram. But it's not the only way, and I wish I had time to tell you about this method. Brian Kibble invented a new kind of electromechanical device, which we now call a Kibble balance, that enables the realization of this definition, again, using a defined value of Planck's constant. You can realize the kilogram. And here's a picture at my institution, at NIST, of one of these Kibble balances that is used to realize the kilogram to about a part in 10 to the 8th, which is better than the amount by which these various kilograms are drifting relative to each other. So now we can start to study what's causing that drift, and that's being done today, and we can be guaranteed that we have a definition of the kilogram that isn't going to drift. Well, all over the world, there are laboratories using Kibble balances, using silicon spheres, including right here in France at the BIPM. In fact, the opening movie showed a little clip of the kibble balance at the BIPM. So when all of these experiments all over the world agreed on their results, then the international community agreed to change the definition of the kilogram. And it was in Versailles in 2018 that the General Conference of Weights and Measures made that agreement. 60 countries of the world agreed unanimously to do this, and they showed this movie.
140 years.
Groundbreaking science.
And the agreement from the world's scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it.
Ce l'abbiamo fatta.
We have het geschafft.
Lo logramos.
neyse böyle.
我们做到了。
Biz buna nail olduk.
Proud om daar.
Biz bunu жасадық. Het is ons gelukt.
Вы сделали это.
انتصرنا. Vi gjorde det.
Америка.
我们成功了。
Mi smo to učinili.
Dokázali jsme to.
أنجزناها.
سويناها.
Congratulations.
축하합니다. Felicitaciones.
Mazal tov. Congratulazioni.
Shate lavorisce.
Selamat sukses.
Parabéns.
Ongera.
Omedeto.
감사합니다.
Onneksi olkoon.
Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
Yes. I hope that many of you recognized your own languages in that video. Some of you may recognize yourself in those videos. And every time I see that, even today, I get emotional, because 60 countries of the world at that time, 60 signatories of the Convention du Metre, agreed unanimously to do something for the good of the entire world. And it was not easy. There were lots of disagreements about how this was to be done, but they did it. They did it unanimously. They did it peacefully. What a wonderful inspiration for how we ought to take care of things in an international way. Well, it wasn't just mass. The ampere was redefined in a similar and very quantum way. It used to be that the ampere was defined in terms of the forces between current-carrying wires, and now we've defined the charge of the electron. And since current is simply charge per unit time, it means that the ampere is a certain number of electrons. Now, we don't do it that way, or at least not yet. We're working on it, but we do it a different way, because with both E and H defined, the Josephson constant, 2E/h in volts per hertz, and H/E squared in ohms are now exact, and we can use the Josephson and the quantum Hall effects to measure all of our electrical quantities. But there's more, 2 more units. The mole used to be the amount of substance that corresponded to the number of entities that is equal to the number of carbon-12 atoms in 12 grams of carbon-12. You all learned that in high school chemistry. But now, it's just a number. We've defined Avogadro's number, and what a wonderful way of bringing the microscopic into this understanding. And then, of course, the Kelvin used to be 1/273.16 of the triple point of water. Now we have it by defining Boltzmann's constant, which is beautiful because it tells us what the energy of one of the atomic constituents of the material whose temperature we're trying to measure. So this is very much at the atomic and at the quantum scale, very much a quantum way of thinking about the international system of units. Well, the French Revolution brought us the metric system, with meters as the measure of all things, kilograms as a measure of mass based on the meter. The Convention du Metre brought the metric system to the world. And on the 20th of May, this very day in 2019, the metric system was reformed in this quantum way so that we are basing our units on constants of nature. And today we're celebrating the blessings of this universal system of measurement that stretches from the French Revolution to the quantum revolution of today, and we're looking forward to more progress in the future. And so this stunning painting of liberty leading the people means, in this context, that we are free of artifacts of standards of measurement, and anybody can realize the standards of measurement. All the base units of the International System of Units are defined by fixing the values of constants of nature. And we're bringing to the SI the dream of those French revolutionaries to have something good à tous les temps, à tous les peuples, for all time, for all people, except, it seems, for time itself. Because time is defined by reference to a specific atom, cesium, rather than to a fundamental constant. The hyperfine frequency of cesium is defined to be this number, and that's what we use to define what we mean by a second. Now the problem is that this is a microwave transition, and using that microwave transition, we can realize the definition of the second in the SI to within a few parts in 10 to the 16. By far the best realization of any of the units of the SI, a few parts in 10 to the 16. But we now have other atoms with optical transitions that can be realized to better than a part in 10 to the 18. So this shows the evolution with time, and I'm running out of time, by the way, of the microwave clocks and the optical clocks. And you see a little bit after the year 2000, the optical clocks took over, and they're just getting better and better all the time. And we are now at a kind of a crossroads where we have been before, where we have to decide how to redefine a unit of the SI, because we now have a technology that is better than the very definition of that unit itself. And we have a wonderful array of possible atoms and possible transitions that could allow this redefinition. Some of them are bosons, some of them are fermions, some of them are ions, some of them are neutral atoms. What are we going to do? Well, later this week, we will have a discussion, and I hope you will all come and be part of that, in which we talk about the possibilities for the redefinition of the second. What is that definition going to be? Well, only time will tell, but those of you who are in charge of national measurement, national metrology institutes, we need your data from your optical frequency standards to be able to make the best decision for this next step in the development of the SI. It's been a tremendous trip. I'm running out of time, and I thank you very much for your attention.